Hello, my name is Elba Leiva, and in this presentation I will mostly cover a brief biography of Claude Louis Navier and George Gabriel Stokes. As you can see in the title, it's Navier-Stokes equation, so I will also talk a little bit about how the equation describes what it consists of and how it is useful for us engineers. Okay, so Claude Louis Navier. He was born on February 10 in 1785 in Dijon, France. He died on August 21 of 1836. His fields of work was mostly mathematical physics, and as the title said before, he made some contributions to science, but what he is mainly known most is for the Navier-Stokes equation. Okay, so let me talk a little more about Claude Louis Navier. So when he was little, his education was mentored by Emilien Gauthier. He was his uncle. Emilien Gauthier was a French mathematician, a civil engineer, and architect. Once when Claude Louis Navier graduated in 1806, he directed the construction of bridges at Juvisy, Asnières, and Argentugo, and he also built a footbridge to the Ile de la Cité in Paris. He started working in the construction because also his uncle Emilien worked as an architect, as a civil engineer. So he went to work with his uncle, and later in life he succeeded his uncle in his work. His bridge building, later, time passed and and something bad happened. His bridge building reputation was destroyed when in 1824 his design for the Pont des Invalides failed to leave a safety margin on top of his calculations, making the bridge crack and be dismantled. So after this happened, Claude Louis Navier had to step back and go out of building bridges and all of this stuff because his reputation was ruined. So after that happened, he started a professorship, and that's when he became a teacher and started working more toward what his contributions in science will be later about. Okay, so as for his contributions, when he was already being a professor, that's when he formulated the general theory of elasticity. In 1819, he succeeded in determining the zero line of mechanical stress, correcting Galileo Galilei's incorrect results. In 1826, he established the elastic modulus as a property of materials independent of the second moment area. Later, as we know him now, mostly is that he is considered to be the founder of modern structural analysis. But even though all of his other work was done, his greatest contribution still remains to be the Navier-Stokes equations. Now to talk a little bit more about George Gabriel Stokes. So he was born on August 13 of 1819 in Scone, Ireland. He died on February 1 of 1903. His work fields are mathematics and physics, and he's known for, as we said before, the Navier-Stokes equations, the Stokes theorem, Stokes law, Stokes shift, Stokes number, Stokes problem, Stokes relations, Stokes phenomenon, and Stokes parameters. Later, I'll try to briefly tell you a little bit more about what does each of what he's known for describes. Now, to talk a little bit about his early life. So George Gabriel Stokes was the youngest of 6 children in an Anglo-Irish family. That's when his first education started. His father was a rector to the church. So not continue what it was intended to be as part of his family, like 3 of his brothers went into the holy orders, so they continued into the church. But Gabriel Stokes later, at the age of 16, moved to England and he entered the Bristol College. During that time is when his talent for mathematics was really shown. For he won several prizes and several recognitions about it. In 1841, Stokes graduated as a top first-class degree in the mathematical theories. After graduating, Stokes followed the advice from a professor of the time of his college to research more about hydrodynamics. By 1842, it was when he started his investigations by analyzing the steady motion of an incompressible fluid in 2 dimensions. So now, let's talk about his contributions to science. So, I told you before that he was known for several stuff. So, as for the Stokes term, the Stokes terms is used in vector calculus, and it's generally differential geometry. In this term, it's stated the integration, it's like there's a statement about the integration of differential forms on manifolds, which both simplifies and generalizes several theorems from vector calculus. Next, we go into Stokes' law. So in 1851, George Gabriel Stokes derived an expression for the frictional force exerted on spherical objects with very small Reynolds number in a viscous fluid known now as drag force. This is like the law. This is derived by solving the Stokes flow limit or small Reynolds numbers of the Navier-Stokes equations. So as I said before, later we'll talk a little more about Navier-Stokes equation. Stokes shift. This is the difference either in frequency or wavelength between positions of the band maxima of absorption and emission spectra of the same electronic transition. The Stokes numbers. This number is a dimensionless and is used to characterize the behavior of particles suspended in a fluid flow. So in fluid dynamics is where we mostly can find the Stokes problem, that is also known as the oscillating boundary ledger. This determines the flow created by an oscillating solid surface. Also, it is considered one of the simplest and steady problems that have an exact solution for the Navier-Stokes equations. The Stokes relations. In physical optics, they describe the relative phase of light reflected at a boundary between materials of different refractive indices. They also relate the transmission and reflection coefficients for the interaction, the Stokes phenomenon. This is the asymptotic behavior of functions can differ in different regions of the complex plane. The Stokes parameter. This is a set of values that describes the polarization state of electromagnetic radiation. It defines as an alternative to the more common description of incoherent or partially polarized radiation in terms of total intensity, degree of polarization, and the shape parameters of the polarization ellipse. Now, the Navier-Stokes equations. So as for this, in fluid mechanics, it is a partial differential equation that describes the flow of incompressible fluids. This equation is a generalization of one devised by Euler in the 18th century to describe the flow of incompressible and frictional fluids. In 1821, Claude Louis Navier introduced the viscosity element for the more difficult and realistic problems of viscous fluids. Later in time, throughout the middle of the 19th century, Stokes improved Navier's work, thus the complete solutions were only obtained for two-dimensional flows. Navier-Stokes equation. So as you can see in the picture, you'll see the equations. So now let me tell you a little bit more like what it consists of and what we use it. So it provides an accurate approximation of reality in situations where there are no strong temperature gradients in the fluid. So this equation consists of a time-dependent continuity equation for conservation of mass, three time-dependent conservation of momentum equation, and a time-dependent conservation of energy equation. The equations consist of four independent variables: the x, y, and z spatial coordinates at some domain, and the time t. Mostly, these equations are used to model the weather, the ocean currents, airflow around an airfoil, and water in a pipe or in a reactor. The Navier-Stokes equation, in their full and simplified form, helps with the design of aircraft, cars, and nuclear reactors, also the study of fluid flow, and many other things. Thank you.